All right, ladies and gentlemen, welcome back. We're talking about the regression line, the best squares regression. And in the last video, we talked about residuals and the role that they played in creating that line and showed some examples. In this video, we're going to actually talk about finding that slope-intercept form equation that creates the least squares regression line. So way back in the day in algebra, you learned this equation, y equals mx plus b, and that was the slope. And this was the y-intercept, and that this equation explains all lines. Well, we use slightly different notation in statistics, but the foundation here is the same, okay? The b sub 0 is the y-intercept, and notice that we tend to put that one first, and the b sub 1 is the slope, again, we write that afterwards, but it's essentially the same thing here, okay? Notice also that we use y hat. We use y hat instead of y to emphasize that the points that we're looking at on this line are predicted values, not actual data. So this is the predicted value of things. We're saying that this model is our predictions about the data set that we have that follows a relatively straight line. If it's a good model, then the data values will be scattering closely around this line, okay? So the b sub 1 and the b sub 0 are the slope and y-intercept of the line. B sub 1 is the slope. It tells us how rapidly the change in the predicted y value is changing with respect to x. The b sub 0 is the y-intercept. It tells us where the line crosses or intercepts the y-axis. We can use the things we know about slope and correlation and about correlation and standard deviations to find the slope. So here we have a formula to find the slope, and that's r times the standard deviation of the y set of values divided by the standard deviation of the x set of values. Notice that you've got the y divided by x, much the same thing as slope here. You're taking the standard deviation, or the average distance from the mean for each of the data sets, y divided by x like slope, and you're scaling it with the correlation in order to find the slope of the line, okay? So we can find the slope of the line by taking r times the standard deviation of y divided by the standard deviation of x. And slope is always in the units of y per x. For y-intercept, we're using the means and the slope. So the y-intercept is the mean of the y set minus the slope, which we calculated in the previous formula, times the mean of the x set, and our intercept is always in units of y. This, by the way, is hand calculating. We will show you, or I will show you how to do this on a calculator in just a moment after we finish this. So, as an example, we have the Burger King data set here. The mean protein content is 17.2, right? That's our x. And the fat is 23.5. That's our y. The standard deviation for protein is 14 grams. That's our x. And the fat is 16.4. That's our y. And if you remember correctly, the correlation is 0.83. So let's find the slope and y-intercept so we can find this line. Y equals b sub 0 plus b sub 1 x, right? And remember, it's y hat. So we need to find the slope first. So b sub 1 is r times the standard deviation of y over the standard deviation of x. And I have all of those ingredients here, right? My correlation is 0.83. My standard deviation of y is 16.4. And my standard deviation of x is 14. So my slope is what I get, when I do those calculations. So 16.4 divided by 14 times 0.83 is going to give us 0.97. So my slope is 0.97. My y-intercept, remember, was b sub 0 is y hat minus my slope times x hat. So this is going to be 23.5 minus 0.97 times 16.4. Oops. No, sorry, 17.2. I did that wrong. 17.2. Nah. All right. Okay, so 0.97 times 17.2. That's going to be 23.5 minus 16.68. And 23.5 minus 16.68 is 6.82. So my slope is 0.97 and my y-intercept is 6.82. Therefore, the equation for this is y hat equals 6.82 plus 0.97x. And sometimes, instead of writing it in terms of y and x, it actually is beneficial for us to just write it in terms of the variables. So we can say fat hat equals 6.82 plus 0.97, and then that's times protein, right? Instead of writing the variables, we can actually just write out what those things are supposed to be. All right, so we can use our formulas to find the slope-intercept form equation, okay? Yeah, so then we can also, if we needed to, this is rounded on the y-axis here, but we could also just, if we wanted to figure out like the predicted content, so let's say we've got 30 grams of protein in that BK broiler sandwich, and we wanted to find the predicted, we could take that 30, plug it in for protein in our equation, and then just solve for it to get 35.9. All right. So by hand, that's the least squares regression line. Let's do on the calculator. Okay, so here we're using a TI-84. I've got a list of data in here. The data comes from a data set that is it's very positive that we did in Chapter 7, the manatees killed versus powerboat licenses. Okay, so I have a stat plot for that up here, a scatter plot that we've created. So what we want to do is find the least squares regression line of this data set. So what we're going to do is go to Stat, Calc, and then all of these things that say reg, right, they are regression. So there's lots of different types of regression. The only type we're going to cover in this class is linear regression. So notice there's two, linreg ax plus b and linreg a plus bx. The only difference in, I don't know why they have two of these. There's probably a decent story behind it. This one, the a is the slope and the b is the y-intercept. If you do this one, it's the a is the slope and the b is the y-intercept. I don't know why they do two of them, right? We could probably Google it and find out, but I'm not going to right now. So I'm going to do this one, and it's going to take list 1 and list 2 as inputs, and there it is. So there's the slope, and there's the y-intercept. Now, what this particular thing is missing, normally it tells us the correlation and the what's called the R-squared. There's a thing you have to do, and it's called turn your diagnostics on. In some calculators, you can hit mode, and this would be the newer TI-84s, and it shows up on here. So if you have a newer TI-84, you're going to see something down here that says diagnostics, and you're just going to want to make sure that that says on. If you don't have a newer calculator, you're going to need to use the command to do it. So the command is down here in the catalog button. So we say second 0, And this is a catalog of every single command on your calculator, and we're looking for the one called diagnostics. So we're scrolling down to the D's, and there it is. Diagnostics on, diagnostics off. We want to turn them on because when you turn them on and then do the same linear regression command, notice it gives you a little bit of extra information here, including the correlation and this thing called the R squared, which we'll talk about a little bit later. Okay. So now that you know how to find it in your calculator, let's talk a little bit about assumptions and conditions that need to be made to make sure that this can happen. Okay, so since regression and correlation are related, it's the same conditions that we checked to make sure for correlation. That is, do we have two quantitative variables? Is it straight enough? And are there any outliers? So check to make sure that there is that the two variables you're dealing with are quantitative variables, not categorical ones, right? Make sure that you're not dealing with the percents. Make sure that your figures have units to make sure that those are quantitative. If we're talking about categorical variables, you cannot do regression, okay? The linear model assumes that the relationship between the variables is linear. Your calculator does not distinguish a difference when looking at a set of data. You can give it a completely non-linear set and say make a line from it, and it will. So if your scatter plot is not straight enough, then you should not be using a linear model to do that. So you want to check your scatter plot before you do any kind of linear regression. You need to check the scatter plot and make sure that it's linear. Again, if your scatter plot's not straight enough, you should stop. You can't use a linear model for any two variables, even if they're related. There has to be a linear association. There are some non-linear relationships that we can save by re-expressing the data to make the scatter plot more linear, and we will talk about that in the future. So there is a way to sometimes take non-straight lines and just fiddle with them a little bit to make them straight enough that we can do a linear relationship. So that's a thing that we'll talk about in future chapters, okay? So straight enough there. But then, again, outliers. The outliers dramatically change a regression model, just like they dramatically change a correlation. They dramatically change what the regression model can be. So if you see outliers in your data, that's also a huge red flag to not do that. Finally, the last thing that you kind of want to look at is checking the residuals. And what you want to do is look for a residual plot and that has a sort of a similar spread, or just a random spread on the residuals. So what is a residual plot? Well, let's go back to the calculator and I will show you what a residual plot is. So when you do the regression command, when you do that linreg command, your calculator saves a list of data for you that is the residuals, right? So if you hit second stat, you come down here to resid. That stands for residuals. Your calculator, every time you do the linear regression command, saves the residuals for all of those points in a separate list for you called resid. Now, if you want to see what those actually are, you can go edit and go to an open list. If you highlight the top and then go to that residual and just hit enter, it'll show you the residuals for you. So this is the residual that is created from this point. So all of these ones, notice that there's a large residual there, there's some large residuals up here. We can go down the whole list and see all of the residuals that were created. We can see how close each of these points are to the, what am I trying to say, to the predicted model, okay? However, we have this thing called a residual plot, which is a scatter plot that uses this residual list. So if you go back to your scatter plots, but this time change the list, your Y list, to the residuals, you can see a residual plot. So each of these dots, you should kind of think of this straight line across as being the predicted model. And each of these points is the residuals. So the distance away from that is telling you how far away it is. When we look at a residual plot, we should see a scatter. We should see like a sneeze on a page, where just everything goes out and it scatters randomly. We should not see a pattern. If we see a pattern, that is a sign that we do not have a linear model. So a residual plot should be scattered, and you do need to check a residual plot anytime you are doing correlation. So you're going to make like a typical scatter plot on here. You're just going to change the Y list with that residual list, and again, second stat to find that residual list. Okay. All right, and that's everything for this particular video. We've got one more coming from this chapter where we're going to talk about R-squared values, and that's everything for chapter 8. Thanks for watching, and we'll see you another time.